Hey guys, this video is going to cover the photoelectric effect, particularly looking at the data that you can collect, in this case specifically from the PhET simulations, and a shout out to them and a thanks to them for these awesome simulations. This is to me, one of the all-time best examples of collaboration, because in this experiment we have so many different physicists at the turn of the 20th century coming together, not necessarily all in the same place, but covering the same material. Talking about Robert Millikan, Heinrich Hertz, most notably Albert Einstein. So we look at this situation here, and basically what the photoelectric effect experiment is saying, or is showing, is that incident light can physically bump electrons off of a photoemissive plate. And basically that plate is some sort of metal that the electrons are knocked off. Now they call these electrons photoelectrons right here. Photo having to do with light, and then of course electrons because they're electrons. And they're not a different kind of electron, they're just identified that way so we know where they've come from. And the main finding of this experiment was that it was not the intensity that caused the electrons to be bumped off, but more so the frequency of the light that was incident upon the photoemissive plate. And that was something huge and something new, and it relates to the idea that we talked about in regards to Planck, because it related energy to frequency. And we know that this is by the proportion of Planck's constant. So this is a very important idea. The data that you would collect would look something like this. Alright, so this data is as simple as that. Alright, I have a picture of Robert Millikan's data from 1914, I believe. Let me pull that up. Nope, I was wrong, 1916. Either way, this is kind of cool because it's looking at his actual data from this experiment. And if we look at what are on these axes, we have frequency over here. This is the frequency of the incident light. And this is the maximum photoelectron kinetic energy. So it makes sense. If I bump something, in this case an electron, and it's freed from the metal of which it was a part, it obviously has gained some kinetic energy. So in a lot of ways, it's almost like the light is doing work on the electrons and changing their kinetic energy. So if we look at this, there's a few very important things that come off of this graph. So I'm going to get rid of the graph really quickly. Alright. And we're going to look at it from this perspective. So we know that it is a linear shape. And it has a very specific y-intercept. Okay, it's negative. And that's very significant. So this axis is labeled for the kinetic energy maximum, and this axis is labeled for the frequency of the incident light. So I'm going to replace the variables. Okay, let's move this over a bit. I'm going to replace the variables with the ones from the graph. So on here we have the maximum kinetic energy. I'm just writing KE to save space. But the maximum kinetic energy, this is equals some slope number. So I'm going to put in a number sign here, the hash pound sign, and x is the frequency. And this minus here, if we think of any y value, y-intercept, it's just an initial y value that has the same label as the y-axis. So I'm going to label it as initial energy. Now I know it's not kinetic energy because that is, there's no value there, right? It's very specific to the situation. But what it turns out is that if you graph lots of different metals, you see this line shift vertically, up or down. So that implies that the initial value, or the y-intercept, is dependent on the material that I'm looking at. Alright, so let's go to a new slide here. So the equation that we have so far is this maximum kinetic energy of the released photoelectrons is equal to some slope value, which we'll get to in a second, times this frequency minus some initial value that is dependent on some metal. Now, what we came to name this value over here is, which we use the Greek letter phi, first of all, and this has become to be known as the work function. Alright, and this is the amount of energy needed from the light just to break the electrons free. So if we think about what's happening here, if you were to look at this term and this term, okay, each term has to be measured in an energy unit, right? So basically what I'm saying is, here's a certain amount of energy, I subtract a certain amount of energy from that, and I'm left with this amount of energy. So if you think of it not as a function from a graph, but purely as a arithmetic equation, this is what you might say. I have 100 apples, I give 23 away, I'm left with 77. But in looking at this in a different way, this can actually be a function in and of itself, right? So let's shift that up and take a look at what that could mean. So it's basically saying, here is some value, all right, of energy. Now, this is energy that's coming from the light source, right? This is energy that's coming from the incident light. And that amount of energy minus the amount of energy, we're using this symbol phi, the work function, minus the energy needed just to break the electron free, will result in us knowing the amount of kinetic energy that the electron has once it leaves the photoemissive plate. So it's purely like, this is the amount that it takes before I can even consider how much kinetic energy the electron has. So if now we know this has to be an energy term, what equation has this relationship? Planck's equation. Max Planck's equation fits perfectly into this scenario. So I'm going to scoot this up again and we'll take a look at what it looks like in its final form. And that is the average kinetic energy of a photoelectron, the maximum kinetic energy of a photoelectron is equal to the amount of energy from the incident light minus the amount of energy it takes to break the electron free. This is a material-dependent variable, or constant, I should say. This is Planck's constant. This is the frequency of the incident light. And this is, of course, the average kinetic energy, or the maximum kinetic energy, of the photoelectrons. So this is the photoelectric equation. And it's so simple and so beautiful and so descriptive of what's going on that you can't even imagine something better used to describe it. Let's take a look at just one last thing about the units of this. The units of the photoelectric equation are, of course, could be measured in joules. But when we're talking about extremely small values, where we're dealing with electrons, for example, if we talk about the amount of work done to change the kinetic energy of a particle, recall that we discussed that could be Q delta V, right? That's the potential difference and the value of the charge. And Q delta V, all right, scoot that up. Q delta V can be written in this sense because it's an electron, specifically E delta V, or just EV. So you can see here that if I look at this in a different way, the units of a joule can have some relationship to what we call an electron volt. Alright? So let's come up with an idea that can maybe get us a conversion factor. Alright, the amount of kinetic energy that results from some amount of work done, we want to measure that in joules. Now we're going to do it in terms of the voltage, the potential difference. Okay, so E delta V, more commonly EV. And I'm going to say the amount of work that it takes to move the charge of an electron across a 1 volt potential difference. So the amount of work it takes to move one electron, whether the field or an external force, across 1 volt. Alright, we could plug that in, right? We could plug in all the values that we need and find a conversion factor from joules to electron volts. So we can say we're looking for the amount of work or energy needed to move an electron, which has an absolute value charge, the elementary charge, 1.6 times 10 to the negative 19th coulombs, across a 1 volt potential difference. So in other words, 1 electron volt as a unit is equal to 1.6 times 10 to the negative 19th joules. Now that's a very small number of joules. That's the amount of joules it takes to move an electron across a potential difference of 1 volt. So instead of writing these things in extremely small scientific notation values, we're going to write all them in values of the electron volt. So for example, if we think of different materials and the work function, right, we can usually list the work function in terms of, we could write that it takes 4.08 electron volts worth of energy just to break the electrons free from the metal. And you could convert that into joules by just using this simple conversion over here. Alright, and you can see there'd be a very tiny amount of joules that's needed to do that, but it makes more sense to write it in electron volts. So the bottom line is, an electron volt is a measure of energy. One or two other variations of the photoelectric equation can be done along the following terms. So what we could write is maximum kinetic energy is equal to HF minus phi for the work function. That's one option. All right. Now another way we can structure this that we know is that the energy can be equal to HF, but it can also be equal to HC over lambda, because F is equal to C over lambda. Now what that allows us to do is to look at HC over lambda here minus V. So we can look at this graph in terms of the wavelength rather than in terms of the frequency. And we have a cutoff frequency or cutoff wavelength, which is specifically when the kinetic energy value, when y is 0, so it's the x-intercept, and the x-intercept is the specific value, which is called the cutoff threshold or cutoff frequency. So the cutoff wavelength, threshold frequency, the threshold wavelength, there's a whole bunch of different terms that you can use. But you can see you can relate things in many different ways, so that we can look at things from different perspectives. Additionally, what you can write is that instead of writing the kinetic energy, you can write things in terms of an electron volt equals HF minus phi. And basically what that allows you to do is look at what voltage would be required to, even if you orient it in the right direction, to prevent those photoelectrons from leaving the plate. All right, and you probably played around with the PhET simulation and saw that that was possible. So all in all, what you should be able to do is, if somebody asked you to find an experimental value of Planck's constant, basically you could plot your data in the photoelectric equation and solve for the slope, right? The slope of any material should still be Planck's constant. So the line will just shift up and down, and that will change this y-intercept. It will also change this x-intercept, which are two values that are dependent upon the material in question. I hope that video helped a little bit, clear up some misunderstandings. Now would be a good time to start working on applying this knowledge to some practice problems and situations.